That'd be hilarious. You're like, nobody who's not here can learn. Stop it. I'll get you people relaxing at home. Alright. So what's fx? 2x minus 4. And you know, this is going to be what? This is going to be 4 minus x minus y. So it'll be plus 2 times 4 minus x minus y times, what's that? Negative 1, I like it. Good old chain rule, I like it. So pretty cool what happened. So 2 came down, that was easy enough. But then this one I'll be able to be a little careful because the inside has a coefficient on x, so I have to use chain rule. Good old fashioned chain rule. Because this is just a partial one. So you get fx equals 2x minus 4 plus 8, no, minus 8, stupid minus, plus 2x plus 2y. So you get fx equals 4x plus 2y minus 12, I believe. Alright, you guys do fy now. Why? Do you notice how for fy, that piece, because for fy, won't this piece be the same, exactly the same? Yes. Look for that, so you don't repeat your work. People always tell me, why'd you make the test so long? I didn't make it as long as you made it. You made it longer than I wanted you to. So fy will just be, the only difference would be there will be a 2y here instead, right? So 2y and 2y is 4y, so it'll be 4y plus 2x minus 8, looks like. You guys see that? Simple? Or if you didn't do it that way, you should end up there anyway. So I need both of those to equal 0 at the same time. So what can I do? Again, I really want you guys to realize this is just a system of equations we've set up. What is it when I have several equations that all have to be true at the same time? It's a system of equations. I could do substitution, I could do elimination, I could do guess and pray and check. No, don't do that. So for example, from this one I know that y has to be yes, 6 minus 2x, is that cool? And over there I can cut things in half, so 2y plus x minus 4 equals 0. I can plug that in there. This is the kind of stuff you should just be able to get your teeth into. Just power through it. Take this, plug it in there. I'm going to get 12 minus 4x plus x minus 4 equals 0. So I get 3x equals 8. X is 8/3. Yeah. All right. And of course, once I know x, I can plug it back in and get y. 6 minus 16 thirds.
Or you can just do it with relational on form.
Yeah, I like it. So remember, matrices, reducing matrices is a way to solve systems of equations. Sure. So y equals, let's see, 6 minus 16 thirds is 18 thirds minus 16 thirds is 2 thirds. I like it. All right, let me stop there for a second. So we know what inputs for this plane cause the distance to be shortest. Right? So if they ask me what point on the plane is closest to this, and actually we don't even know if it's closest. What do I have to do to make sure that this is actually a true minimum? Yeah, the big D, right? The big, not the little distance one. Right, so if you did all that, you'll find out it is a minimum. So if you plug it back in to what's the real question asking? It's just asking to do what? Yeah, find the shortest distance. So you got to plug x and y back into your distance formula. Actually, take a square root. You can do all that in the calculator. I mean, now the calculus is over. Now it's just plug stuff back in and calculate what it is. Right? That's where I kind of lose interest. Yes.
Why don't we use the formula D for the absolute value of x that function over square root of a squared plus b squared plus c squared?
Oh, okay. You could. That was the distance between. You're talking about that little one at the end of that section from a while back.
Oh no, chapter 12.
Yeah, that found the distance between a line and a plane, right? No? It was a point and a plane? Okay. Oh, yeah. If you really wanted to, you could. Because it's more disgusting, for one thing.
Isn't it the shortest distance too, because it's like perpendicular to the plane, so it should be the
so this is let me see. Oh. Yeah, it depends on how you plugged it in there, I guess. I mean, it should come out to be the same. It is the shortest distance formula. It's just not one that we use a lot. It should come out to be the same answer.
Right, so if you use that, like what points would I plug in for a...
Ah, so that's where things get interesting. Yeah.
So if you plug in principal point or the actual point?
So this would be your point, right? Yeah. Okay. All right. So last thing for today. I like that. I wasn't trying to say that. It sounded like you went, but I don't think you did that. That would be really throwing me off if you did. Okay, so everybody got what they want from this here? Okay. So again, to remind you guys, I made 14.8 extra credit. So before I let you out of here today, I just want to talk a little bit about what we're about to get into. Chapter 15 is double integration, and of course, after that we can do triple integration. So it's actually multiple integration. What do they call it? Multiple integrals. I like it. That captures the idea. Oh shit. So, let me start off with an example from Math 180. Oh, I almost forgot. Shoot. I'm so excited to get into this. Let me do one example of, I might not be able to get to chapter 15 today. Damn. Alright, before we leave section 14.7, I guess I should show you this. This gets a little bit gross. So the absolute max and min value thing that you did in Math 180, I just had to give you an interval on the x-axis. Now I've got to give you some shape in the xy plane. Oh, what? So let's do an example. Let's see here. Well, let me give you kind of an outline of what's going to happen. We find critical values. And evaluate them there.
Probably not this good.
Then we find, now this is what's going to happen. They're going to say, find the absolute maximum values on the surface, but only over, maybe it would be nice if it was just a circle or something in the, or even just a squarish region. So remember, critical points only occur at those like tangent plane and horizontal positions. But for absolute max and min, it doesn't have to have a critical point. It just, so back in Math 180, obviously that would be a max. This looks like it wants to be a min there, but that would be the absolute min there. Right? And that would be the absolute max. So the absolute max, the absolute min could occur at a critical point, but they don't have to, because the endpoints could actually get lower or higher than they do. So it's really just evaluate everything and then just step back and see who won. Who won the positive race or the bigger race and who won the smallest race, right? Don't get to me about, well, your race analogy breaks down with big and small. Screw it, you know what I mean. Don't overanalyze my grammar and all this. Find extreme values on the boundary. And then determine the winners. The biggest and the smallest. All right, so here's an example. I like it. So step one is, now don't forget, I'm giving us pretty easy functions to work with at the moment, but you also have to find critical points where those function derivatives are undefined. That's the possible location of a max or a min also, right? This one's just polynomial in nature. It's not going to be any undefined stuff. So step one, find the critical values and then evaluate all those. So what critical values do I have here? What's fx? 2x minus 2. What's fy? 4y minus 4. I made this remarkably nice. So what's the only critical value? 1, 1. Critical point. 1, 1. Sorry. I don't know if you remember this. Do I have to do the big D stuff for this? No, big D stuff doesn't matter or shit. That's the beautiful thing about the absolute max and min way back when you were in Calc 1. Was the worst part was calculating the second derivative, especially when it was a quotient rule or something like that. They had to plug stuff back in and see if it was less than 0, or you had to make the number line, all that kind of crap. Absolute max and min, you find critical values, you look at the boundary in this case, and then you step back and see who won. What's the biggest, what's the smallest? So what is a function evaluated at 1, 1? What's the value of f of 1, 1?
1 plus 2 minus 2 minus 1 is -3.
Yeah, we get 3, 1, -3 plus 1 is -2. Cool. The second step is where things get weird. And the second step is why I won't be able to do chapter 15. Oh, I didn't tell you this. This would help for the second step. Find the critical values. Find the absolute extrema for this function over this region. So it will be the region like this here. Obviously drawn beautifully to scale. Okay. So I like this problem because it's relatively easy, but it also shows you what you have to consider as you do this. So what does this function become if I follow this boundary? And I don't care about the middle. The middle is what the critical point takes care of. I really want that to make sense. In the inside, the only place it could be a max or a min is at a critical point. It's at the endpoints, which now becomes the boundary of my... So it used to be endpoints back in Math 180. Now it's the boundary of the region that they want me to consider. Oh shit. So maybe it does something like this, and there's a nice maximum here, and then it goes, whee! So there's an absolute max over there at the edge. All right, maybe. Now what's nice about 1-1, now that I've given you the full problem, 1-1 actually lives inside there. So just like you had to do back when you did absolute max and min in 180, if the critical point you find is not in the region they want you to consider, you can throw the damn thing out. In fact, you have to throw the damn thing out. It's not a candidate. There's no chance. It's related to a person that works there or something. You got to throw them out.
What would you do then?
You don't look at it. It doesn't. It's not one of the. So if this would have been 4,1, I would have just said, "Oh, there's no critical values to worry about. Critical points." So if I am on this, so I want to look at my boundary, right? So if I'm letting x go from 0 to 2, I want to look at all these boundaries here. And I'm letting y do what it wants to. Right? So in that case, what am I looking at? I want, for example, how am I going to say this? F of, yeah, that'll work. F of 0y, F of 2y. What's F of 0y look like?
2y squared minus 4y plus 6.
And that, let me make sure you guys are with me here. So that's looking along 0 to 2 for x. Now I can look at that like a normal two-dimensional function, right? Where's this guy's max or min happen? What kind of thing is this? Parabolic. It's max or min. In fact, in this case, it's going to be opening up, so it's going to have a min. Where? Yeah, how do you find? Remember, negative b over 2a. Or you can do derivative. Right. So now what I'm doing is, what does this function look like along one of these boundaries? So if x is 0, it looks like this. If x is 2, it looks like, well, we're going to figure that out in a second. And then I just look at each of those functions and see what's the max and min for those. Yes, sir?
Can you also just get all the critical points and then from there look at your domain restrictions? Just like, let's say like you have a critical point that's like you're going from 0 to 2. Let's say like you have -1 and 5.
Well, then you throw that one out.
Out of the bounds, you can just scratch that critical.
Of course, true. But that's not an also question. I would have done that here if there would have been, but that won't change what I'm doing right now.
Right.
Yeah. I still got to do this, unfortunately. It's too bad. This shouldn't be that bad. Where's the minimum occur for this? -4 over -4 is 1. And what's the value of this at y equal 1? 2 minus 4 plus 1 is -1. So we have -2. This guy has a minimum at -1. So please go with me. So above this box, there is a piece of this surface, right? This surface, whatever it looks like, or below it even, because it could be a min. But I'm only concerned about the outputs that are on this surface that are coming from inputs inside this box. So that's this step. That takes care of the inside. Now I'm trying to take care of the outside. So I've got to look at, what if x is 0? What if x is 2? What if y is 0? What if y is 3? That's my endpoints now. That's my boundaries now. Yes?
If you get a function with the max and the min on one side. Like, because we found the min because it was a...
Yeah, that could happen all day long.
But
Totally.
what if you have something that does this?
Totally. You could have all answers existing on one side. Sure. Why not? Because you could have, like, it could be like parabola, and then it goes up here, and then it goes down, huge down. You know, so you could have absolute mins and absolute max all on one border.
So then do you need to determine like which side
No.
is the biggest?
The beautiful thing is, you do what we're doing. You collect. See, I've collected the number -2. That's a potential min, absolute min. Can't be an absolute max because that's bigger, right? This is a potential absolute max. So let's see if we get something bigger or smaller than what we got so far. What about what's this going to look like? Along x equal to 2, it's going to look like 4 plus 2y squared minus 4 minus 4y plus 1.
So it's the same thing.
Same thing.
Yeah, same thing.
That's nice. I've already done that work. So that border, that boundary gives me only this as an entry to the competition. Yes, sir?
What about the endpoints? What's the endpoints of those boundaries?
Let's keep going. So that's for this and this. I'm sorry. That's for this and this. Now we got to do this and this. What's this guy determined by?
Y equals 0.
Y equals 0. So if y equals 0,
X squared.
what's f of x 0 look like?
X squared minus 2x plus 1.
I like it. And what does f of x 3 look like? X squared plus 18 minus 2x minus 12 plus 1. So x squared minus 2x plus 7. Looks like, right? So again, this max, min, sorry, is going to occur at its vertex, right? Oh, I see what you're talking about. You mean the other ends. Yeah. So you do have to worry about those. Yeah. I try to fit all this in here at the end. So this one, the min, we still got to go back here and look at the maxes in this. The min would happen at -2/2 is -1. And -1, when you plug a -1 in, what do you get? You get 1, 1, 4, 1, 1,
Negate it.
5.
Be positive 2 instead.
Yeah, 1 plus 1 plus 2 is 4.
No.
No.
It's negative b over 2a.
Yes.
So it's
So
positive 1.
x is 1. Yeah, okay, I'm with you. 1 plus 1 is so it's 0. And what about the maximum here? Well, what's the min x and the max x? What's the smallest x can be? 0. The biggest x can be is 2. All right. Let's take a step back. Let's not try to jam this all in at the end. Yes?
I have a question. When you translated the y equals negative b over 2a, wouldn't it be a positive one? Because negative b would be a negative.
Yeah, it is a positive one.
Oh.
And then this is the reason I circle this is because it's a candidate for the biggest or the smallest.
Why is negative 1 here?
Because when you plug a 1 in, what do you get?
Oh, okay.
Yeah. All right, so let me not try to jam this in at the end. I know you guys are all like, oh, shit. But the actual work of this isn't too bad. It's just another thing to kind of get used to what you've got to consider. So I'll do another little handout with an explanation. It's too bad we don't get to these. We'll do these. Man, I was so excited about chapter 15. We'll do these. It's very colorful for me. We'll do those next time. Okay. Yeah.
For, sorry.